So in this question, we have a graph, and we'll do our Oy-Zerga analysis. So first thing is the origin. We'll start here, 10, 8, 6, 4, 2, 0. And then 10, 5, 0, 95, 990. Whoops, this thing is not at 0, 0. It's residing somewhere like this in quadrant 1. So it's not at 0, 0. Y-axis velocity in normal units, x-axis time in normal units. We can read velocity in time. The gradient is delta v over delta t, which is the acceleration, and the area is v delta t, meters per second times seconds, which is the displacement. Now, looking at the gradient being the acceleration, we can look at ship 1, and the slope of that would give the acceleration, and ship 2, the slope of that would give the acceleration. We notice that ship 2 has a positive acceleration, where that means the velocity is increasing, and ship 1, it's got negative acceleration, and we also see that the velocity is decreasing in magnitude. So now we read the problem. Two identical spaceships, and the identical means masses are equal. Far from any planets or stars, that means there is no interaction with other bodies. The entire system is the two ships, and there's nothing else. They travel in the same direction, the slower one directly behind the faster one. So the faster one, which we can see just from the numbers of the velocity, is ship 1. And the slower one is ship 2, with lower velocities, although the velocities are eventually coming to be equal with each other. All right, so the ships are connected by a cable attached to a spool. So there's a cable, and that spool allows them to change the length of the cord, the cable between them. And the purpose is that it brings the ships to the same speed for a transfer of cargo. So then it might stand to reason, if these two things are tied together, that the faster one is going to lose speed and the slower one is going to gain speed as they both end up with the same speed. And that's exactly what we see, the faster one decreasing and the slower one increasing. Now, of course, if we look a little more closely, once they have the same speed, what we expect to happen would be this. They would go off with the same equal speed. The graph shows the speed. Does at least one of the ships have its engine turned on during the time shown, and what evidence? Well, in this situation, we would expect the momentum of the system to remain constant. Does it? They both have the same mass, and for ship 1, the delta P is m delta V. And let's say the mass is m, and the change in velocity is 5. So the change in momentum is minus 5m. For the green one, we have a delta P equal to m delta V. And the mass is m, and the velocity goes from 790 to 8,005. So the delta V is positive 15, so it's 15m. So it seems that the green one gained more momentum than the blue one lost. And how could that happen? It needs to have the engine on. So we say yes, which would take this out because it's no. Ship 2 is speeding up. Well, ship 2 is speeding up, and that does look like it's true. It is a true statement. Yes is correct. This is a true statement. But is it evidence? We have to be careful. Yes is true. It is true that 2 is speeding up, but that's not how we know that. We don't know it based on the speed alone. It's about the momentum. So we want to be careful. How we just came to that conclusion, of course we knew the thing was speeding up, but how we came to the conclusion wasn't about the speed. It was the speed showed us that the momentum gained by the one wasn't equal to the momentum lost by the other. The next one, yes, because the momentum of the two rocket system increases. Well, that is true. The momentum does increase. This one decreases by 5, and the green one increases by 15. There's a net increase in 10. So it looks like B, and then C, because the engine is needed to keep the system moving, that is false. In outer space, a rocket turns on its engine, gets up to speed, turns it off, and it goes in that direction forever. Choice B.